field D2 charged infinite plane sheet. Here field will be only due to surface 1 and surface 2 because for other surface area vector and V vector are perpendicular to each other. Here you see Gaussian surface. Here this is the Gaussian rectangular pipe, this whose surface 1 and surface 2 has area A, and surface charge density is sigma of plane sheet. Now net flux of electric field is phi equals to phi 1 plus phi 2, hence equals to E vector dot EA vector equals to 2 E vector dot A vector 2A cos 0 degree equals to 2 EA, question 1. And charge enclosed by Gaussian surface, that is Gaussian rectangular parallelepiped, equals to Q. Charge enclosed by Gaussian surface is Q equal to sigma A, question 2. From Gauss's law, total flux is equal to charge enclosed by epsilon naught. Hence 2 into E into A equals to Q by epsilon naught equal to sigma A by epsilon naught. This implies E equal to sigma by 2 epsilon naught, or E vector equal to sigma by 2 epsilon naught n cap, where n cap is a unit vector normal to the plane and going away from it. Next, field due to uniform charge thin spherical shell. This is a spherical shell of radius r and which is given charge q and whose charge density is sigma, surface charge density is sigma. Field outside the shell. First, flux through the elementary area ds vector is d phi vector equal to E vector dot ds vector. Hence net flux through whole surface is phi equals to integration of d phi equals to integration E vector dot ds vector. This is Gaussian spherical surface we have considered, or equals to integration of E ds cos 0 integration E ds integration E into integration ds, or equals to E into S, or equals to E into 4 pi r square, equation 1. Now charge enclosed by Gaussian surface is Q into sigma 4 pi r square. Hence from Gauss's law, total flux is equal to charge enclosed by epsilon naught. Hence E into 4 pi r square equal to sigma into 4 pi r square by epsilon naught. This implies E equals to sigma cap r square by sigma by epsilon naught r square equals to E equals to sigma into cap r square by epsilon naught r square equals to Q by 4 pi r square, putting the value of sigma, into cap r square by epsilon naught r square equals to Q by 4 pi epsilon naught r square, or equal to 1 by 4 pi epsilon naught Q by r square. Hence E vector equal to 1 by 4 pi epsilon naught Q by r square into r cap. Thus for a outside point, a spherical charge shell behave as a point charge placed at its center. Second, field inside the shell. Here a Gaussian surface is drawn inside the shell. Here it is shown, this dotted line, and point P is at a distance r from the center O. Taking OP as a radius, we draw a Gaussian sphere as shown in the figure. From Gauss's law, phi equal to Q by epsilon naught. This implies integration E vector dot ds vector equals to Q by epsilon naught. This implies ES equal to Q by epsilon naught. This implies ES equal to 0 by epsilon naught equals to 0. This implies E equal to 0 since S is not equal to 0. Thus the field due to a uniform charged thin shell is 0 at all points inside the shell. Electric potential energy U. It is the energy associated with a charge distribution due to its configuration or position of charge in the electric field. It is also defined as the amount of work done by external agent to bring any charge from infinity to the given point in electric field. Whenever the configuration of the system changes, the potential energy of the system changes. The change in electrical potential energy is equal to the work done by external agent in changing the configuration of the system. Here we see that this is the initial configuration in which Q1, Q2, Q3, Q4 charges. So initial potential energy UI. When an external agent does work on this system, the configuration changes, and this is the final configuration. So final potential energy of this system will be UF. Hence, we can write UI, initial potential energy plus work done by external agent equals to UF, final potential energy. This implies del W external initial to final equals to UF minus UI equals to delta U. Note, in changing the configuration, the acceleration of the particle is kept 0. Potential energy difference delta U. The potential energy difference between 2 points is the work done by external force in moving without acceleration any charge from one point to another for electric field at any arbitrary charge configuration. Consider a test charge is moved from R to P. This is R and this is P. This is a Q which is test charge, and this is capital Q is source charge by the external agent. The work done by external agent in moving charge from R to P is delta W R to P external equals to integration R to P F external dot dr equals to minus of integration R to P F vector dot dr, since F external equals to minus of F vector. This implies change in potential energy delta U R to P equals to UP minus UR. Potential energy at a point. The work done by external agent to bring any charge from infinity to that point is called potential energy at that point. That is, potential energy at point P is UP equals to delta W infinity to P, limit infinity to P external. Again from the definition of potential energy difference, delta W external limit infinity to P equals to delta U limit infinity to P equals to UP minus U infinity. From 1 and 2, UP equals to UP minus U infinity. This implies U infinity equal to UP minus UP equal to 0. That is, the potential energy of a charge at infinity is 0. This is called reference position of charge. Now del W external initial to final state equals to minus del W electric field initial to finals equals to delta U initial to finals equals to UF minus UI, or equals to integration initial to final limit F external dot dr equals to minus of initial integration of initial to final F vector dot dr vector. Electric potential. Electric potential at a point in the electric field is defined as the work done by external agent to bring the unit positive charge at that point. Thus, Vp, which represent electric potential at point P, potential at point P equals to delta W external infinity to P by Q equals to delta U infinity to P by Q, where delta W external infinity to P is the work done in bringing the charge Q from infinity to point P. equals to up minus u infinity by q equals to up by q because u infinity is 0, or vp equals to up by q, or in general v equals to u by q, where v is the potential and u is the potential energy, or u equals to q into v, or delta u equals to q into delta v. Here v is up minus u infinity equals to q into vp minus v infinity. For example, delta u r to p equals to q into delta v r to p, or up minus ur equal to q into vp minus vr. Hence vp minus vr equal to up minus ur by q. Potential due to point charge. dwf external dot dr dash, we are considering a point at distance r dash from plus cap q charge, that is source charge, which is placed at o, and point p is at a distance r, and p dash is at a distance r dash, and at p dash there is a unit positive charge. So we are calculating first work done on unit positive charge. So ddw equal to f external dot dr dash equals to f external dr dash equals to q by 4 pi epsilon naught q into 1 by r dash square into minus of dr dash, or equals to minus 1 by 4 pi epsilon naught q by r dash square dr dash. Hence w equals to infinity to p dw equals to infinity to integration infinity to r minus of q by 4 pi epsilon naught r dash square into dr dash equals to minus q by 4 pi epsilon naught integration infinity to r dr dash by r dash square equals to minus q by 4 pi epsilon naught under bracket minus 1 by r dash limit infinity to r minus q by 4 pi epsilon net equals to 1 by r dash limit r to infinity to r equals to minus 1, or equals to q by 4 pi epsilon naught under bracket 1 by r minus 1 by infinity equals to 1 by 4 pi epsilon naught q by r. Hence Vp potential at P equals to 1 by 4 pi epsilon naught q by r. That is potential at a distance r due to charge q is given by Vp equal to 1 by 4 pi epsilon naught q by r.